Hello, my name is Austin Burbridge, and I am reviewing and analyzing the article titled "A Survey on Data Center Networking, Infrastructure, and Operations." Since internet services and applications continue to grow, data centers have become necessary to handle the huge demand that current services require and traditional networks cannot handle. Data center networks have allowed organizations and businesses to manage ever-growing networks without them becoming prohibitively expensive. This paper is about the unique problems that data center networks have in comparison to the traditional ways of managing networks such as local area networks and WAN. One of the challenges is simply that large-scale and exponential growth of recent networks. For example, Microsoft has to host over 1 million servers and 100 data centers with ease, reliability, and cost efficiency. The data centers must be able to handle a wide variety of services like webmail, web search, games, distributed file systems, and distributed execution engines. Each of these services has different traffic signatures. Recently, data center networks have received significant attention from businesses and universities because of these challenges. This article is about the various publications and surveys on data center networks to provide a more balanced view. Data center network infrastructure. The data center network infrastructure connects nodes in a single data center and between them. There are two ways we can talk about this: transmission technology and scale. Transmission technologies. Currently there is wireless, electrical, and optical transmission technologies available to us. There's been a shift away from electrical methods to optical methods currently because optic fiber is becoming cheaper, has more bandwidth, and consumes less power. If we want more flexibility, we can also opt for wireless networks. The recent increase in wireless speeds is allowing them to become more common in large-scale networks. Electrical cables have bandwidth ranges around 10 megabits per second to 10 gigabits per second. Downside is that they are direct current, so the signal can only travel 100 meters before dying. Second technology is optical, typically in the form of optical fiber. Optical fiber can transmit at a higher bandwidth, lighter weight, and lower power consumption than electrical transmission. Networks are not just limited to just two wired technologies. They can use a combination of the two. Electrical switches, gigabit interface converters, and SFP can be used to bridge the gap between the two technologies. Because wireless technology is achieving greater bandwidth, it is becoming a viable option for data centers. I will talk more about that in the analysis. Intra-data center networks serve as the connections between devices in a data center. They must be customizable by master user as well. There are three types of transmission technologies that can be used for intra-data center networks. There are electrical element-based topologies, electrical/optical element-based topology, electrical/wireless-based topology. Electrical element topology is still the main choice today. Electrical element-based topologies are based on the electronic switches. Electronic switches are fast to set up, and they're often compatible with old systems or legacy systems. Electrical element-based topologies are either switch-centric or server-centric. Switch-centric means switches conduct data transmission. Switches are formed into hierarchies. Fat tree is a type of network architecture shown here. Fat tree is useful because switches are cheap and there are various equal cost paths between hosts. Another type is VL2 shown here as well. VL2 is also cheap. In VL2, the network architecture between the core and aggregation layer is a bipartite graph, and edge switches are connected to the two aggregation switches. Finally, Jellyfish is another network architecture shown here, which uses a degree-bound random regular graph at the edge layer. Jellyfish is adaptable to new expansion because a server within Jellyfish can contact more servers in fewer hops than a fat tree configuration. Here are some server-centric topologies in which servers not only act as end nodes, but also relay nodes to other servers. There are three common hierarchical structures for server-centric topologies: D-cell, B-cell, Vicon, shown in the figures below. These arrangements allow for more efficient use of the network. Data center network operations are the operations that make running network hardware infrastructure and data network possible. Data center network's primary goal is to get data from source to destination. Currently, each switch learns the topology of the network with forwarding tables. The path the packet takes is based on protocols like spanning trees, VLAN, routing algorithms, multipath routing, OpenFlow, and encoding path information. Unfortunately, I don't have enough time to get into the details of these technologies in this presentation. Path selection, rate limiting, and priority management can be used to achieve a greater utilization of networks by finding optimal paths. It has been shown that there is currently low link utilization in inter-data centers and intra-data centers. Hedera is used to direct large flows based on future estimations. Edge switches detect large flows by measuring bandwidth occupation threshold. Path allocation is determined using a simulate annealing-based algorithm. We can also use B4, which has a high bandwidth for inter-data centers. Swan can compute traffic paths in order to optimize the network. Data centers must share physical resources to meet their needs, but competitive users can unfairly enhance their network speeds by creating multiple TCP connections or using UDP. There are two ways to divide performance. Those who can pay better get better performance, or there's minimum bandwidth guarantee where users is guaranteed a minimum bandwidth. Here's a table of various bandwidth allocation schemes. Some are bandwidth guarantee and others are bandwidth proportionality, which are the paid ones. Services like video games, social networking, and search generate low traffic but require low latency. Explicit traffic control restricts information to flow deadlines or flow sizes. Deadline-driven delivery, or D3, uses deadline-aware rating allocation to manage flows. PDQ uses current rate paths, RTT, deadline, and expected transmission time to determine the correct sending rates. L2 DC2 changes the size of the TCP congestion window. In addition, LT DC2 follows least attained service scheduling. Due to environmental concerns and ever-growing data center workloads, energy consumption has become a more critical issue. There are two general ways to reduce power consumption: intra-data center optimization and inter-data center optimization. Turning off idle network devices is a good strategy to reduce power in intra-data centers. Elastic Trees has a power management tool which can do this. Small link rate can also lead to low power consumption. There's also Green Tea, EPRA, and combining with VM placement are other strategies to reduce power consumption on intra-data centers. A data center must be accessible to identify network failures and monitor the activity of the data center. OpenFlow flow tables can be exported from data centers. SFlow can monitor and sample packets. ZUpdate uses lossless transition sequences. NetPilot automatically deals with a network failure by maneuvering around the failure instead of outright fixing it. There are still challenges to overcome in data center networks. Multicast is where you send data from source to multiple destinations. Currently, multicast is plagued with many problems and can be used in data networks without encountering issues. In addition, there's cross-system optimization, which is where a data center can benefit from cross-system cooperation and optimization. You can put modular data centers on shipping containers in order to deal with millions of servers. There's also MD Cube, which is a modularized data center cube, which is created with the B cube. MD Cube uses a hypercube topology for intercontaining networking. There's also Merchant Silicon Switch, which can be used as building blocks for data center networks. Silicon Switch, a single switch, contains a massive number of ports. This reduces the complexity required for cables. And finally, there is software-defined networking, which is what is currently used and very likely to be researched more in the future. SDN allows networks to be more programmable by allowing dynamic network devices. That's it for the summary section. Now I will talk about my analysis of the paper. This article is good for anybody just starting to learn about data centers. It covers a wider range of concerns and the solutions to them. However, if you want a detailed look at the solution schemes, you have to look elsewhere. This article only provides brief descriptions of the technologies. The purpose of the article is to make you aware of these technologies so you can research them yourself. I did some more reading in some of the technologies that the article did not go into much detail about. One is the wireless links used for the purpose of data center network infrastructure. Currently, wireless transmission is used outside the data center and hasn't seen much use between servers in a server room. But with the development of faster wireless technology and the static and dense nature of server rooms, wireless links may supersede wired links. Wireless connections are much more adaptable and reduce the complexity of organizing fiber optics and electrical cables. And with the addition of 60 gigahertz millimeter wave technology, these wireless links are becoming more feasible. One downside, though, is the signal noise ratio in 60 gigahertz frequencies is quite large, about 55 decibels worse than 2.4 gigahertz. This is because higher frequencies have higher free space path loss. In the paper Augmenting Data Center Networks with Multi-Gigabit Wireless Links, the authors ran a test in which data servers use TCP flow with wireless 60 gigahertz links. Servers were in a free space environment. Large fluctuations in throughput and data rate are common with other wireless systems like Wi-Fi. Fortunately, their results show that data rate was stable and variation in throughput was 0. Because the wireless transmitter sits above the server, as people walk by, they are below the line of sight. One thing that the paper mentioned, but did not go into much detail about, was the problem with using multicast in data center networks. Multicast is whenever you send data from a single source to multiple destinations. I read the article Dr. Multicast, ARCs for Data Center Communication Scalability, to better understand the problem that prevented it from being used in data centers. When data centers grow, they tend toward one source to many destinations type services. IPMC, IP multicast allows a message to send multiple destinations with a single operation. However, data centers today do not use IPMC because of the issues with it. IPMC is vulnerable to denial of service attacks. There's also a scalability problem. Communications networks and data center is shared by all applications, therefore filters become ineffective. Hosts start receiving huge amounts of unwanted traffic. Receivers have to start dropping packets. IPMC will only work if they have a centralized command that can control the number of groups on the network. Another problem is membership churn. Membership churn occurs when a new node enters the network. Another issue is that some IGMP switches will ignore new members if there are already too many members in a group. Other IGMP switches will forward the IMPC packets everywhere on the network. It has been shown that IGMP v4 multicast group can only handle around 70 and 1500 groups before packet loss becomes too much.